first part will be about a competition that took place, well, like, I don't know, 8 years ago now. It's a bit longer ago, but it's the nice thing about it had some practical aspect and so on, and was driven by the Department of Energy in the US. So it was deemed to be important. That's like an introduction in the sense, okay, here, this is what we can do with it. Then I have a part that talks about an optimization algorithm. And the last part is a bit more newer researchy, where I talk about like a project. So if you understand the second part, the third part, hopefully will also be followable. Here we go. So I say large scale optimization. So when I wrote down optimization, I thought, okay, so what I didn't say, so my background is mainly continuous optimization. So I will talk mainly about continuous optimization. If we have time, I bring something in that I stole from a colleague, where we have some examples of discrete aspects. But I mean, many of the problems that we have that I'm going to talk about also can be made more complicated with discrete methods, but I'm not going to talk about that very much. Oh, and if you have questions, please interrupt me. And I also feel like not only zoning out at the beginning. Okay, so this is what I want to talk about. So ARPA-E, the Advanced Research Project Agency for Energy at the DOE, had a competition some time ago. And they said, okay, so what we're going to do is we want to have researchers that are usually working in academia and so on, see if they can actually do something practical. And practical meant not writing a paper, but actually producing software. So you're not measured on your own experiments, but we look at what you do to see if you actually did a good job. And they wanted to do this to make sure that, you know, they work on the resilience and security of the American power grid. So there were teams that could, what they had to do, they had to develop algorithms for a practical problem. They developed the algorithms. They had to implement it in software that then was independently evaluated on problems that were, well, most of them were synthetic, but developed specifically during this program also to capture the real characteristics of the power grid. And then there were also some proprietary networks that they've tried it on. So, well, I don't need to show you this, but I just, okay, so when we have the electric power grids, we have generators, we have loads, we have transformers, we have power lines. There are different layers, of course, of the systems. You have the transmission system, and then you have distribution systems. And just to set the context here, so this was about large-scale transmission systems. We did optimal power flow. That's what this is about. So you need to make sure that you meet all the demand. And the power that you generate, you should simply do at the least cost. Okay, so that's the typical optimal power flow problem. But of course, in practice, the ISOs have to plan what do we do when something goes wrong. So the security constraint optimal power flow problem is basically the same problem, but it says, you know, things can go wrong. I can have a generator that fails. I can have a transformer that goes out, or I could have a line that goes away. And of course, what happens is if a transformer goes away, you don't have enough generation, so you have to kick in and make more generation, or if you curtail demand and so on. But of course, you still have to make sure that the grid is then operated in a safe way, that you still satisfy the rating constraints, the lines don't get too hot, etc. And so the competition considered the n-1 contingencies. That means you say you have your regular network, and a contingency means that one of those elements goes away. So a transformer could go away, or a generator could go away. And so n-2 contingencies would be where two things go away. Of course, that makes the whole thing more complicated. But this competition considered these cases. Any questions? So the organizers was ARPA-E. So they said this: the goal of the competition is to accelerate the development and development of transformational and disruptive methods for solving what they said is the most pressing power system problems. Okay, so they thought it's important. They said, okay, what we want is we want to have a fair comparison of algorithms that should be like industrial grade, like really sophisticated and robust. And we will test them on real large difficult problems. And so the idea was, I guess, that they said, okay, so maybe out of this comes new research that then we can use and then implement somehow in reality, some software company or maybe some of the entities that participate in the competition will, bring this forward and make this commercial, and then actually will be used. And it will be organized in multiple challenges. So they started at, what was it, 2018, I think. So there were 3 challenges. The first challenge is what I'm going to talk about, because a group and we together participated in there. So that's where I had most of the experience. But then there came 2 more challenges where things then became more complicated and so on. I can maybe say a few words. I have a colleague who participated in both of them, the other ones really well, and meaning he made some money and can maybe tell you what he did. Okay, so the first challenge is security constraint optimal power flow. And usually what's done, this is solved in the linear version, where you have represent the power flow with linear constraints and linear relationships. So that's DC. What was important here, they said, well, no, that's not accurately describing what's actually going on. We want to make sure we capture the real system, and we want to look at the nonlinear AC formulation. And that's where the challenge is. So the belief is that, no, that's too complicated, we can't do this. And their goal was to figure out, is that really true? Is it really not possible to solve these problems in real time? Or if we just, get some people to really focus on this, can we get this so that it can actually be useful? And so they say here that if these enhanced STOPF algorithms, they can offer like 5 to 10% reductions in the total electricity costs, and enhance here means also looking at AC, savings of that many dollars and so on. So this is from their website. So what I took away from this is that they say we put a lot of money into this. We think this is important, and let's get researchers that are usually not involved in this in there. And my hope was, okay, so then great, then we're going to do something, and then people will pick that up and will use it. So, well, I should maybe tell you later what came out of this. Okay, so this is the perspective with which we came in here. Okay, so what I tell you is, how was this competition set up? What was the mathematical formulation? How different teams approached it, how they solved it, and I also will then tell you how we did this. And yeah. So the competition was set up in this way. So anybody could participate. And there was money to win, but only US entities, so universities or private people or companies could actually get the reward. And some of the teams got initial funding. So when we said we want to participate, the DOE said, okay, so we're going to give you some money, write a proposal, we give you money, and nice, we can get summer salary. In the US, you have to get summer salary, right? You get summer salary and you can fund your students. But then if you win, you can use it as your further funding. If you went in there and didn't get this initial grant, you could just take the money home. And my colleague, who was working at Los Alamos at the time, he was trying to convince his employer, hey, I want to do this. Can we do this together? And I said, oh, that's too complicated. We don't know. He said, okay, then I do it as my own. And he could keep the money. And that is turned out to be a really good decision. So the submissions, or what you do is you come up with your algorithm, you submit the software, and then you don't give them any description or anything. You just give them a code, and then they run it on instances that you haven't seen. They give you, of course, test instances and so on that hopefully reflect, what the algorithm is going to see when they're testing it. And here is like the timeline of this, of how that looked like. So there was a start date that was in November 18, and then there was you had to register at a certain amount of time. Then there were different trial events where they said, okay, so we give you some instances, do something, and then it's like a test, and give us your code and we run it and let's see how good you're doing. Okay, you didn't win anything. It's more like, who's doing the best right now, and there was a race and whatever. And it also turned out to be really important for them, because they didn't know what's going to happen if they had some ideas, okay, when you get these submissions, this is what we have to do. And, but I mean, it's hard to anticipate what happens. And one thing they learned at the first time is that when they were evaluating the submissions that they hadn't considered how long that would take. And after the first trial, then they realized, but I think there was a period where it was like the most, so they run this at Lawrence Livermore high performance computer cluster. It took most of that thing just because they needed to evaluate the submissions from the competition. And they needed to do this because they didn't give any rules what people would give them for the evaluation. So it was good for them to see, oh, no, we're not going to do this way. So not only us, also they learned from what was going on. And there were 3 trials. And then eventually, like a year later here, there was submission. And then a month later, the results were released. For me personally, that fit perfectly because I was going on a sabbatical at Los Alamos, just in the middle of 2019. And one thing that as an academic you really want to do, but you can't, is write code. So there I could just write code. I could focus on this and do something that that unfortunately you would usually never be able to publish. Right? I think code is unfortunately something that's hard for us, for those people who like it. So here is how that looked like, how the prizes looked like. So they said we have 4 boxes here where you can win money. And they said is, okay, so one is we evaluate your code in real time, meaning you give us your algorithm and you have 10 minutes, do whatever you want. And at the end of this, we are looking at what you gave us. And they said we have 2 different ways to evaluate it. One, so the same solution, but evaluated in different ways. One is just lowest cost, then averaged over many instances. And then the performance profile, which looked at some more like timing and so on, different characteristics, and just give you another measure. And then what they said is, okay, in each of these boxes, the top 10 get $100,000. So if you're among the top 10 in all of them, you can win $400,000. Now imagine you're doing this as a private person. That gives you a house. So we had got our seeding funding. So when we got we were among the first 10 as well. So we had funding, which was then nice because we can continue working on this a little bit. So the total means we had $4 million of prize money. That was for the first challenge, and it was going further. So that's pretty unusual that the funding agency says, okay, here's a competition. You can make this money from it. Also, what I thought was really clever to say, we don't distinguish between the first 10. Because people like me, I'm a nonlinear optimization person. I work on algorithms, but I'm not really working on power systems. And I would never have thought, if the first 10 gets, first 3 win something, I would never have thought, I have no chance. Yeah, I know about optimization, but I don't really know that much about power systems. I learned some now, so which I hope allows me to talk here. That was really clever because this way they got people involved that usually wouldn't dare to do this. So, but there were some companies that involved, but also just academics that never would have looked at this. And so so there are 26 participants. Here is the top 10. So the first team is a team from Lawrence Livermore. From Lawrence Livermore. That did really well, and I will talk about how they solved the problem. That was pretty clever, I thought. This is us. We were the second ones that I forgot now where everybody is from. This is my colleague who did this on his own time, and then there's some other entities that were participating. Any question? Okay. So you needed 10, benchmarks, how to test this on, how to, play around. You needed to play around with when you were developing it, etc. And what they did is they said, okay, before they started with this competition part of this thing, they spent several years just having funding researchers to just figure out how to make synthetic, realistic transmission system data. So that was coming to an end here. So we then had 17 different synthetic networks. They were ranging from 500 buses to 30,000 buses. They were really trying to mimic what's going on in the real world, not like IEEE, whatever, but harder. Then in terms of the contingency, so what they would do is they would say, okay, here's your network. That's your base case. And then they say, okay, I give you a set of contingencies where like this transformer is out or this generator is out. Okay. They didn't say you have to take every single thing, but they gave you contingencies. But for the large networks, they gave you up to 20,000 contingencies. So in 20,000 cases, you still needed to make sure you have something, a solution that works. I'll tell you a bit more about this. And then for each network, in the submission, they said, okay, we give you 10 different instances, meaning different loads and with different loads and configurations. And then in addition, they had 3 proprietary networks that after we never saw, even after the competition, we couldn't see why maybe we didn't do well or anything like this. They were also there. And so, yeah, we had, of course, for these networks, we had some data, and that's maybe the not so realistic part. When you submitted your software, they also would tell you, okay, here's a totally different new network. Okay, so you haven't seen so you've seen other networks maybe of that size, but here's a totally new network, which is not realistic. I mean, if you're developing something like this, you know your network. You don't give your algorithm a network you've never seen before, but you know it very well and so on. But this was assuming that, okay, we just give you any network and you can do with it what you want. In terms of the computing hardware, so they told us, okay, you can use 6 limited nodes that have 24 cores each and 64 gigabytes. Okay, and if you want to, you can use MPI to communicate between the nodes. So that's pretty decent and maybe something that a system operator should be able to afford. And it was hosted at PNNR, so they had used their supercomputers there. Later parts of the competition actually went down to, at the end of the day, you just have one computer, you have less time, you have much more complicated problems, and you still have to solve it. And people were able to figure something out. Of course, the question is, what does solve here mean? You don't solve it anymore. You get something that's reasonable. Software, people could use whatever they wanted. They could use Julia, Python. Nobody used MATLAB. I don't think anybody used AMPL. If you know what AMPL is a modeling language. And then they could use solvers, Cplex, Groby, IPOP, Nitro, so linear, mixed digital linear, nonlinear solvers, and so on. Or you write their own solver if you want to. A solver meaning nonlinear optimization solvers to solve the optimization problems. And then to submit it, you could, they had the web interface, and they gave you, so you could submit jobs to their and computing environment. You didn't have to have 6 nodes, so you could just come up, say, okay, this is my binary right now. Please run this and tell me what happens. It goes in the queue, and if you have a stupid mistake, it takes a while for you to wait, and then you get, oh, you made a stupid mistake, and you don't get any results. So you have to be really careful what you're doing. Okay. Okay, so now the question is, what problems are we actually solving mathematically? Okay, so the power flow equations. So at each node in our bus, at each bus in our network, each node in our network, we have voltage, we have the phase angle, and then we have active and reactive power that flies, that is transmitted between the power lines, or also that's injected into the system. Okay, and then this is just the regular equations that tell you how, given the voltage and phase angles between 2 buses, how much power flows between them. So these are nonlinear equations, not linear, so they're not approximated in like a DC with linear equations, they're nonlinear. Okay, and then of course you have balance constraints that say, what goes in has to come out. Okay, so here, this is what's coming in through it. So if I have a node J, I, okay, what's coming in, what's leaving that node minus what's going into this node has to be equal to what's generated at that node minus the load. Okay, just standard stuff. So what degrees of freedom do you have? What can you control? Well, there's some of the nodes that have generators, and that's what I can control. So I can change what is the, how much power am I injecting here? So that's what you're trying to figure out. What is the right, generation at each of the generators to minimize the costs? Okay, and then they said, well, there's one more thing that you can control, and that is in some of these buses, you have controllable shunts. So I'm not the power engineer, so I assume you know what that is. But it somehow it helps you to change what happens to the reactive power and different buses. So what you could change at each node that had a generator, how much you inject, and you could change in some of the buses these controllable shunts. So that's what you can play with. Okay.
Yeah, just were they like linearish shunt or discrete block?
Oh, so we assumed here that these are continuous.
Okay.
Variables. In later phases, at some point we had tap ratios for the transformers. That's not here. Those were discrete, but no, they were, which is, that was first phase one. So
Yeah,
things were really.
With the last phase where
you did.
No, I didn't, but
yeah.
Switching.
Yeah, so that was becoming.
Yeah, much more.
Yes. But I can talk. I don't want to talk about it because I cannot say too much about that. Okay, so these are the degrees of freedom. Once you fix this, everything else in the system, the state is determined. Okay, so here's the whole thing. We have here, describing how much power flows between nodes. Here's the balance equation. This here is a very important relationship, of course, that tells you that between two nodes, I and J, the line between that shouldn't deliver too much power. Sorry, they shouldn't carry too much power. Okay. Because otherwise it gets too hot. Okay. And so these rating constraints here were, the different ways of formulating this. This is how they decided to formulate this. Okay, so that's a very important constraint. Okay, that's what limits you. That's the congestion, right? And then you had you couldn't produce too much, too little power, and so on. Yes, usually so limits on the power generation, what you could do with the shunts, and also for you had to make sure that the buses, the voltage stays within safety descriptions. So this now is a large-scale continuous nonlinear optimization problem, and you can solve these problems. Okay, a problem like this with 100,000 buses or so, you can solve, and it takes a few minutes or so. So that's doable, or maybe even shorter. And so what does solve? If you have a nonlinear optimization problem, then they're nice problems, convex problems, where you know that, okay, if I find a solution, it's the global minimum. If you have a non-convex problem, something like this, right, then you have two local minima. So you have something here and here. And of course, you want the global minimum. But finding the global minimum of a large-scale nonlinear problem is really, well, it's impossible, or it takes a really long time. It's much easier to find a local minimum. The funny thing is people observe that for these power flow problems, if you have a reasonable starting point, you actually get the global solution, or at least something pretty close to the global solution. So, some people approached this originally and said, okay, we really want to solve these problems. We want to get the global solution. You can't do this. So eventually, everybody basically looked at saying, okay, all we want is just a local solution to this problem, but that's good enough. At the end of the day, you're evaluated at the cost. So if you have a bad local minimum, that would hurt you. Okay, but if you had a good starting point, that was you had a good chance to actually get a good value here. And of course, I'm making simplifications here. Okay. Any questions? Any need for coffee? No? There's really good cheese. Too much left. So okay. We're gonna have a break. I'm gonna have a break between the different parts. Yes. It won't be melted totally, I think. Okay. So now I'm going to talk about how we address this problem. Okay. So we are in an abstract layer. If you just step back a little bit, in terms of the optimization problem, you have a objective function, which was piecewise linear. Piecewise linear means not smooth, but there's an easy way to reformulate this so that you have everything is differentiable and so on. We had equality constraints, which were simply these here, that describe the network. We had inequality constraints that were just the rating constraints, and then of course we had box constraints. Okay. Now, I gave them here different colors because what happens here is that G here, what is in red here, so G means generator. So that's the thing that I could control. That's the thing for which I had to pay. Okay. And another thing I could control is in green here. These were the controllable shunts. Okay. So these are also decisions I can make. And once I fix that, you remember here, once I fix my decisions, the state is determined. So basically, these equality constraints here, then, once I give you G and B, the equations just tell you what X has to be. Okay. And so, yeah, oops, that's what I just said a second. Okay. And and that's important to explain now how the problem and how the contingencies and so on come in. So when you have a contingency, what you can do, so you have your base case, okay? So you decide this is how I run this without anything going wrong. And then when I have a contingency, so if a generator failed, then of course what happens is, well, I'm not producing enough power, so I have to change something during the operation in the contingency, I have to generate more power or something like this, right? But what you also have to make sure, of course, you have enough power, but you're also now not running too much current through a particular power line. So you have to make sure that you're still operating the system in a safe way. Okay. So to address this here, there's the real world and there's what's in the competition. So, and I'm not a power engineer, so I'm trying to explain it as correctly and fairly as I can. So, you have to, you have the base case and the generator fails, some action has to be taken. And they have here a specific way in terms of participation factors, and I'll explain you what that is, what is done. So that's something that can happen immediately, automatically, and so on, and is one way. In the later parts of the competitions, they told you, no, you can actually adjust more freely everywhere, the generators and so on. In this part here, the response was very restricted. So if something happens, you cannot do much. The only thing that is going to happen is that you say, all right, so here is my power generation at the base case, 0. And there's one generator that produces that much, another generator that produces that much. Okay. And now if a generator fails, more power has to be produced. So, and what this says is everybody starts generating more power, or everybody who's participating in this process, everybody is producing more power in a way that is proportional to this participation factor. So you can think of basically having a knob here, delta, that says, okay, something goes wrong, there's not enough power. Now let's increase this delta here until eventually the accumulated power production and so on meets the demand again. Okay? So what that means, that because it's an automatic response, you have no decision to make in the contingency. You set up what you say, I'm doing in the base case when nothing goes wrong. If a generator fails, depending on what I chose in the base case, there's an automatic reaction. It's not that I can, okay, so this generator should produce less, this one should do more, and so on. Very restricted things that you can do. Okay. This is what I'm going to skip here. So that's the response. So now to make a big mathematical problem out of this. So this is the base case where we have the power generation in the base case, G, we have the state there, and then we have these shunts. And there's a reason why they named V. Okay. So when there was now a contingency, which I call K, yeah, then what happens is the automatic generator response should lead to a safe operation for the contingency. Okay. So what happens is, so this basically tells you, computes how this delta should be, what's the power generation in the contingency. Okay. But now the power flow changes, and of course now your rating constraints can be violated. Okay. So that's the problem. Yeah. So you have, if what happens is you choose to produce that much power in the base case, something goes wrong, and your automatic reaction tells you, okay, produce that more, and now you have a rating constraint violated. No, that's not good. You have to produce less power somewhere. Okay, or the voltage at the bus gets too high. Okay, so that's why you had to be careful. Okay, so I'm writing this down here. For each contingency, then, of course, given the base case during the power generation, the state is computed. With the new state, you need to make sure you're satisfying the rating constraints and also here the voltage constraints. Okay, but there was one more thing we actually could play with, and these were these controllable shunts. So the power generation was adjusted automatically, but okay, so there's one more thing you can do to save the world, and it is to adjust these green variables here. So in a sense, the only degree of freedom I have in this contingency are really the green variables. Am I making sense though?
Is a G not missing in the bus? Or?
Good question. G is the power, so G is the power generation in the base case, and I'm not touching
that changes.
Oh, well, actually, good, actually, yeah, so I wasn't quite clear here. So what can happen here is that as you stretch a generator, and now you're saying produce more and more and more, and then at some point it would just hit its upper limit. And the rule here, that makes the rule more complicated. But the rule was basically saying, if you hit this, don't generate more.
Yeah.
Okay, so it's automatically in there, in the response. Thanks, yes. Okay. But of course, what happens, there are contingencies that just cannot be solved. There is just no way of finding a common base case power generation to be safe in every of these 20,000 contingencies. So it's not possible to make sure it's always okay. And also, you only have 10 minutes to compute something, so you might just not be able to find something that's always okay. So they said, well, okay, fine, but you pay for it. So what they do here is they basically introduce these penalty variables and say, all right, fine. So we want this to be less or equal to 0. Okay, well, if it's not less or equal to 0, if it's bigger, then I'm getting this variable t here, which is non-negative. So if this is like 5, then this variable becomes 5. And then it's added up here, all these violations are added up in the objective function, so it becomes a penalty term. So you pay for the violation of the constraints. Okay. So, and if you have an equality constraint here, then you have a positive part. So, you need to look at the positive and negative part separately to capture this. So basically, this is just an L1 norm of the constraint violation. And this is, okay, so first I should say here, the official, because it's a competition and there could be lawyers that sue you, you had to be extremely clear what you're actually solving. So they had the document that described this stuff here, that I had this one here, was 78 pages long. Okay. So there were a lot of things just to make sure, okay, nobody gets this wrong. Why did I say that? Oh, and so this way of penalizing the constraint violation was also theirs. What they said here, let's penalize it proportional to the number of contingencies. So if you had 20,000 contingencies, and most of them are fine, and there's one terrible one, it actually doesn't hurt you as much, which is probably not exactly what they intended to do. But for us, solving the really large problems, of course, said, okay, so if you violate a bunch, it doesn't matter, just make sure the really bad ones aren't hurting that much. So in a sense, the larger problems maybe became a bit easier. Okay. So this is the problem that everybody had to solve, the mathematical problem. And look at this, I don't need. Okay. All right. What's this? Oh. This is now how it worked. So if you told them, here's my program, they said, okay, thanks for the program. Now we are running your program in a first phase in 10 or 15 minutes, and you spit out what your solution is. You tell us what's happening in the base case. You tell us what's the power generation, what chance things do you use, settings do you use, and what's the state. Okay, and they make sure, okay, so that's given, so you can evaluate these things here, and also in the base case you were allowed to violate this. We would penalize, but more. Okay. And then they said, well, in 10 minutes, you probably couldn't look at all the 20,000 contingencies. That's okay. So now in the second phase, you said, all right, okay, now we give you, at the beginning, that was a problem. We give you unlimited time. And then you can compute, you go through all your contingencies and you tell us what is the setting for your contingencies, for your chance, and what is the state that you get from this. Okay, let me say it again. So you're solving this thing. You're trying to get the base case. You're trying to handle all the contingencies. But at the end, you only give them the base case solution. That's what they take. Okay, so that's your answer. And now you have arbitrary amount of time to actually tell us how good the solution was. We need to evaluate this thing here. We're not going to evaluate it. You, as the participant, you have to tell us what are these things that you would actually put into practice. Okay. And okay, so with a looser time limit, at the beginning, they didn't set a time limit. So some people just had extremely stupid ways of computing these things, taking days. And the organizers, because they didn't say, oh, you cannot use that much time, had to just run these whole things the whole time. And yeah, so that bit them. And so going after this, they said, okay, there is a time, you don't have much time to solve the actual problem. But then in order to tell us, Cynthia, what would you actually do in the case of a contingency? You have more time, but a finite amount of time. Okay, so that's basically for every instance that we solved and that they need to evaluate, that's what the process was. And then and then simply, once you give somebody the values here for these variables, they can just look at what's the constraint violation and compute the penalty score. You were never allowed to violate these box constraints. That gave you a huge penalty, but it was easy because they're box constraints. You just make always sure they. Okay. That was the problem. And now I'm giving you an overview of what I tell you how we did this, but also first I want to give you an overview of how other teams did this. And I know some about the approach. So I'm not going to be able to answer too detailed questions, but it was interesting to see what we had our idea and so, oh yeah, that's probably how everybody would do it. No, so people had some pretty good ideas. So, but before I talk about this, so in the competition then, we have, as I said already, there are some instances that had 30,000 buses, 20,000 contingencies. In each, even though it's 30,000 buses, with all the variables that you have, power flow, all this, like one case, the base case or any contingency case is like more than 500,000 variables. So if you would just write down this problem, okay, here, you would have you would have 14 billion variables. Okay, of course, nobody can solve this. You cannot just write, okay, here I'm writing a nice optimization problem in Ampere, in Joule, Jump, or whatever, and solve it. No, of course, that's not possible. So you had to do something to solve these problems in a more clever way. And as I said, there were very short time limits. And they basically said that the 10 minutes is what you have in real time, 45 minutes is how, if you pretend it's an offline situation, what we would do there. And it's difficult because you have nonlinear, non-convex constraints. I didn't talk about these complementarity constraints. I don't want to, it gets me we have 3 hours, so I don't want to overload you totally. But these are constraints that show up in this formulation. They're nonlinear constraints, but harder even. Okay, so they were in there, they made it more complicated. And of course, I mean, they're degenerate, they're ill-conditioned. Degenerate, for example, if you have a power line that's like where the rating constraint is active, there's a good chance that not nearby is also a power line that's almost active. Okay, so an almost active is kind of degenerate. It's hard to figure out. Well, so that's where degeneracy comes up. Okay, how do you solve them? Well, you can't. You don't solve them, right? You simply figure out the best you can do in the time that you have. And you probably didn't find the optimal solution. All you want to do is find a solution that's better than your competitor, right? So of course, you need to exploit problem structure. You cannot just throw it at a nonlinear optimization solver. You need to use domain knowledge. Luckily, on our team, don't have the slide, we had Dan Mozan, which was our power engineer superstar. And we were more the nonlinear optimization people. So he really helped us to understand and what are the tricks we can do to solve them maybe easier. What can we do in terms of specializing our approach? Of course, what's really important is the software aspect. You had to make sure there's no segmentation fault. You had to make sure everything is efficient. You had to do, because you could do parallel computing, you need to make sure you really use the parallel resources well. And all that stuff. And you have to totally forget that you're usually an academic, you need to prove things and all these things. No, now it's more like, is it? So I can say this now because I'm at Northwestern, and my time at Northwestern is ending, and now I started at Gurobi. So the perspective is very different. So I have to write papers as an academic. Gurobi, I have to make sure things work. And often when I was, working on something, it's hard to ask yourself really the question, if I really have to solve a problem, would I solve it that way? How I write it in the paper? And if you're all honest, not necessarily, right? And that's the thing also here, right? You have all these nice ideas, and we wanted to write a paper, but that it turns out writing software takes so much time that you can't really do much else. And also we had nice ideas about the algorithm we wanted to do, we didn't get to it. So at the end of the day, you just do what you can. You have to do tricks that don't go, you talk about this, right? Don't go low with the theory at all. Okay, so of course, you've seen, yes, please.
Is there some teams that publish the code for the competition? Is there some codes that are available also?
Let me make them open source.
Yeah. Okay. Just so you can.
I don't know.
Okay.
We didn't, but that's, not really. But, so the code you write on short time is not the most pretty code, right? So it's kind of embarrassing maybe. And then we thought, the thing was, we thought, okay, there's not, the Department of Energy put so much money in there, so somebody might be interested and talk to you and so on. And once it, no, turned out not necessarily to be the case, but yeah, no, I don't know of anybody.
So you're aware of the work of the other teams because
they talk well, they talked about it. You asked them, or they gave presentations. Mm-hmm. So after this, there was a I forget how it's called, like an event where they tried to get practitioners and the teams together. And I thought, oh, that's going to be great. We're going to talk to people, not many showed up. And it is, even though, me as an academic looking at this is, oh, this is so close to reality. This is like a real problem. But no, there's still a lot of simplifications here that are just not what system operators need to use. So there's still a huge, there's a big gap between what the expectations and necessities are for the real case and that. I don't know exactly what happened after the other two challenges, what happened then, because then the problems became closer and had like things that, because they wanted, you have to start somewhere, and for good reason they did 3 challenges to build it up. And we did, okay, I'm talking about this one because that's the one I can talk about because that's the one we participated in. And we participated, well, okay, yeah. Okay, how do we solve them? You've seen, of course, this has a decomposable structure, right? That's why I tried to emphasize that with the colors here. If you fix the base case generation, okay, then you can just solve this problem separately. What you have to do is you have to make a decision for the shunts, and then you have to compute the states, and you need to make sure that the constraint violation is violated. So that by itself is just an optimization problem. Okay. So you can compute this in parallel. if you say, okay, I'm somehow, while I'm trying to solve this big problem with these like cost functions from the contingencies, okay, I'm doing this maybe iteratively or whatever. At some point, I just have a candidate or iterate or whatever for my base case power generation. Now I can just evaluate what happens to the contingencies. What's the constraint violation in the contingency? That's where your parallel computation comes in. Okay. Okay, sorry. So what was interesting to see is that the contingencies, I mean, these were realistic problems. So they were not made arbitrarily difficult. And what turns out is that there are just many contingencies that are benign. Okay, you have a base case generation, you just plug, that's what it is. Okay, and then you have a contingency, the automatic response happens. No problem. You can solve this. There's no infeasibility here. You can do this. So what that means is there were only a few contingencies that really mattered. If you would know what they are up front, you could just write a version of this problem. There you go. A version of this problem where instead of the 20,000 contingencies, that's if it wasn't the case, but if it's only 5 contingencies, for example, then you could write down the problem with just 5 repetitions of this. And that's a problem that's actually maybe doable. Maybe you can solve this in one go. Okay. So that was an important observation here. Then, okay, so this is the team that won. And hopefully I remember now correctly what I wrote here. They looked at this decomposition structure, two-stage structure, if you know what that means. So the structure, and they said, well, this is a really complicated function. Right? I have to solve an optimization problem to compute what that is. Okay, and if I have an algorithm here for nonlinear optimization algorithm, they usually want derivatives. This function here is not differentiable or anything, even if you compute it and whatever. So they said, okay, let's just approximate this here by a simple function. And they said, by a simple, what do they say here? A simple quadratic function. Okay, so instead of having this whole thing about the having to solve like a complicated optimization problem, just evaluate a quadratic function with 2 variables. Okay, and let me now read what I did here. That's the one slide I've given this before, but it's been and this is the one slide I realized I should have looked at this a little. Anyway, so they were saying we want to mimic what the system operator does. Maybe you can figure this out together. And that is if you have yeah, sure, makes sense. So if you have so you have your base case, okay? And if you have a generator in a contingency that fails, if you reduce what this generator produces in the base case, you of course reduce the impact that its disappearance has on the network. So if it turns out you can just, without having the base case costing much more, if you could switch off that generator, okay, then having the contingency wouldn't do anything. Okay, so they said that, okay, if I have a generator that fails in a particular contingency, okay, I just penalize how much it produces in the base case. And then they said, well, that's just a quadratic approximation. And then they said, okay, so where is it? Yeah. So we have an quadratic approximation of the this base case function. We fix these coefficients here, okay, and then we just solve this problem, okay. But okay, now this might not really be a good approximation. So then they say we now adjust this parameter here, so this one parameter, so that when we actually solve the true problem, okay, that they actually match. So let me say that again. So they approximate this really complicated subproblem by a quadratic function. They solve this problem with this approximation, but the approximation is, of course, just an approximation, might be wrong. To correct it, then actually solve all these things here. They solve them, and then adjust their quadratic approximation and solve the problem again. So the iterative procedure where you solve a nice problem that's only as big as the base problem repeatedly, but each time with a better approximation of your contingency functions. I see people, a few people nodding, so it means I was somewhat comprehensive, whatever the word is. Yes.
The contingencies can be generator failure or line or transformer failure.
Yeah.
Okay.
But to be honest, transformer, I keep saying this. Okay, they were see. So you keep me honest. Okay, yeah. Yeah. I'm not quite sure what they did in the line cases.
But here they minimize the impact of generator failing.
Yeah.
So how do they treat the lines in the same way, but
I don't remember exactly. So this is, I mean, I think there is a paper now, but I don't.
Usually they remove the line. It's the same with but with one line.
Yeah.
And that's what we want to solve. So picture it as you have n-1 problems to solve, and the one solution you'll be submitting needs to be working for each of them.
Yeah.
And then add to that, you want to field the fault.
Okay.
But this.
So they will minimize the quadratic impact of removing the line in that case.
So wait, so there's two quadratic. So the quadratic, you mean the Q function?
Yeah, the Q, we don't see it.
Wrong way. When we're going wrong way.
So if you're familiar with stochastic optimization, you can picture it as a scenario-based stochastic optimization problem. You just stack all your constraints, and you need to find the one solution that works for them.
I'm not quite sure if that was.
I don't exactly.
So the trick here is to pick the one generator that failed in the contingency, right? That's what you're saying?
Yeah, but I was wondering if you treated because you talked about the generator failing.
Yeah.
But I was wondering if it was the same approach for a line failing.
In this, yes, but I don't remember exactly what their quadratic approximation is, because here to pick the generator that failed in a line, I don't know if they pick generators that were close. I don't know, but they did a similar trick. Okay. Then I'm not going to talk about this. So there's first order methods that are specifically for decomposing large scale problems. So it's one team used this. Oh, I should say. So these are the first ones. So they really want. So I mean, this was a nice idea because you kept solving problems of the same size, the base case size. Yes.
I know they won, so it must be good. But did they evaluate the tracking performance of this penalty? Oh, this
they must have, but
exactly. Okay, yeah. It was I guess Sorry.
Yeah. So they did third place with this first order method. Then there were teams that said, okay, well, let's use the DC, or at least a linear approximation of the nonlinear power flows. And then there are tons of methods for doing this. There's Bender's decomposition and so on. But of course, at the end of the day, you needed to give people, needed to give organizers like the state and so on for the AC thing. So you had to then just get them back to the nonlinear formulation. So did the projection of this. And there were teams that did this and got 6th and 10th place. Okay, I skipped that. But just on a high level, there was a company that actually designs computer chips, digital circuits. And they said, we just map the big transmission grid and pretend it's a big digital circuit and use all our software and all our strategies to do this. And then we pretend that somehow we're doing an interior point algorithm. Okay, they got somewhere. Okay. And I mean, they were really, that was their business. They're really trying to push this and say, hey, you want our stuff? Please buy it. I mean, so this is kind of an example where people used to gain knowledge, didn't really know, I think, that much about optimization, did this algorithm, into your point algorithm, maybe not how you do it, but again, you got something out of it. Okay, so now our approach. So this is the people that participated. Dan Mozan, he's now, I met him when he was at Argonne, he's now at Georgia Tech. This is a colleague working on nonlinear optimization. Elizabeth Wong if you know what SNR is, it's an only optimization algorithm. So was, I think she left part of the developer team here. These are us from Northwestern, non-optimization, network analysis, and way and optimization. This was our PhD student who's now actually at LinkedIn. So she graduated in the meantime. All right. Our approach, just kind of what I told you already. I said that it turned out that most of the contingencies were benign. Okay. So we just said, let's just guess which ones are important. So we had a way of we had some. So if I wanted to write a proposal, I would say, hey, we have an AI model, we have a machine learning model, we have a linear regression model to kind of guess what are the infeasibilities from a contingency, right? So to rank them up front. So we picked a bunch, and if you have a smaller instance, then you can pick more, and otherwise you cannot pick that many.
Just a question. It's really about finding the most sensitive variables, right? The ones that the problem is most sensitive to. Is it?
The most, yeah, it's right. So you want to know what generators, the failing of which or line is, yes, correctly. So we were trying to figure out for each generator what kind of score, what impact would it have, what infeasibility would it get us, so it's trying, I forget exactly.
Function theorem, is it the way? Is it right to think about it like that? Because you don't know the derivative, but you want to estimate the variation.
Yeah, I mean, it's a discrete thing, right? The generator is gone suddenly.
Yeah,
right? So
it doesn't vary locally.
Yeah, so this is all just trying to make things work, right? And we tried what we could. If we had more time, we probably would have done something better. At the end of the day, just make sure this MPI thing doesn't crash in the last minute. I mean, like software stuff, right? Okay, so we had an initial guess of the critical contingencies. Then we said, okay, let's just solve the problem with these critical contingencies. Okay, and that gave us a first base case thing. And then we said, okay, now let's evaluate these. Let's see how good our solution actually is. Let's fix this intermediate thing and let's solve these contingency problems. Again, you cannot solve all 20,000. We ranked them again. I mean, in parallel, we ranked these problems, had a time limit and so on. And in the end of that time, whatever. Then we said, okay, fine. Now we have a new set of contingencies. We now solve a bigger master problem with more contingencies. So it grew until as much as we could. So the nice thing about the other approach, the first one I showed you, is that the problem that they solved was always the same size, the base case problem. So, I mean, Cosmin, who was driving this, is a power engineer. He is a high performance computing person. So he really knew what he was doing. We kind of knew what we were doing. And a similar, my colleague friend, he also did something similar and he got 5th place. Okay. Let's see. So these are details that maybe I don't need to go through. So this talks about how we selected the contingencies, the trick, how we once we fixed the G0 here, so base case production, how we very quickly evaluated some of these contingencies, figured out, oh, they're actually benign or anything like this. But I think that now goes too much into detail given the time that we have. So is there anything maybe at the end that's important? Well, okay, showing off. So our code was relatively big. And one advantage that I think we had compared to others maybe is that, so if you do nonlinear optimization, the algorithms need derivatives. They need first and second. If you really should give them second derivatives. And there are tools that do that for you. You can write software like an ample or a jump or whatever, automatic differentiation tools, they compute this for you. But that can sometimes really take quite some time of the function evaluation. What we did instead, we just evaluated them. So we just said, okay, so I just have code that gives you the gradient, that gives you the second derivatives and so on. So that really made a big difference here. We used IPOP, but I'm going to talk about in so next thing we talked about, we did this. You had to use parallelization, and to make it as most efficient as we could, we had these 6 workers. Okay, they were talking by MPI, but each one internally had P threads, and there was like a master worker setup where we had one node was running IP-opt for this big problem, and in the meantime, all the other ones were running these sub-problems and evaluating these contingencies.
So,
Yep.
was it like running asynchronously, and when you detect a contingency, you were stuck with
Yes, it was.
problems?
I have this here. Let me go back to this. So you're solving this problem. You're solving this problem here for a set of contingencies, right, that you chose. Then you need to evaluate, given the solution you got, you need to evaluate, oh, what are the bad contingencies? And usually you would have to wait until then have the new contingents and then solve again the new master problem. But that was a lot of idle time. So we were a step behind, if you know what I mean. So when we screened for new contingencies, we used a base case solution while we are already computing a new one. So it was a bit of a mismatch. And then the evaluation, the evaluation was totally asynchronous. So that's what. Okay, so I have a slide for this. I don't know. So, okay. So in this evaluation, for the evaluation of these contingencies, this, at the beginning, people had as much time as they wanted. But so once you had these 10 minutes and you gave them, here is the base case information, then they ask you, okay, now compute for every of the contingencies, please compute what is the B that you choose, what's the X that you choose, and so on. And they gave you 140 seconds or something like this per contingency, which sounds like a lot. But actually, it turns out, no, it's not a lot. If you have these large problems, some of them actually take long. And at the end, it became also a competition about who can do, not solving the original problem, but who can do this contingency evaluation fast enough. If you didn't finish that in time, your score was 0. So there was an unintended consequence from from putting a time limit there, but okay. That's actually what I think I just said. So that was the phase 1. So phase 2 then was a bit later, and that's where you then also actually could have unit commitment and transmission switching. So you could switch generators on or off. The important thing is, and then in the contingencies, you also now have to, instead of just constraint violation, you have to consider the generation cost and so on. Okay. And you had a much more flexible recourse action. So instead of having this automatic response, which is totally limited, so it really mattered what you did in your base case, now you had a much more open decision. So you just couldn't, ramping constraints, you just couldn't change the generation by too much. But that means almost no matter what you did in the base case, you could always fix what was going on in the contingency. So we participated in this thing, and essentially by ignoring the contingencies. And that, for many people, that gave already a pretty good solution. So that was, again, an unintended consequence, I think. And we, with the discrete decisions, we simply solved the DC version with the unit commitment problem, just using Gurobi or Cplex or whatever we were using at the time, and so on. And then came the real challenge, where you then have multi-period, I think 48 time steps that are linked. Again, contingencies. You have discrete decisions. I'm forgetting one thing. But that really required you to come up with heuristics and tricks. So my friend, he basically, for the discrete decisions, he used a rounding technique, but in a very clever way, by rounding important decisions first, resolving a continuous problem, relaxation, and so on. Okay, now I'm starting to talk a bit too much. Okay. Any other question here? Then I will go to the algorithm part. This is now something different. We have, so I talked about like power system application and so on. Now I'm talking about just an algorithm, okay? And that's the algorithm we use to solve this. And it is the algorithm that the next thing is based on, okay? So, and what I want to do is, so there's probably quite a variety of how much background people have. So I have a intuitive, hopefully, intuition of what a presentation of what optimality conditions are. And then I just want to explain this into your point algorithm on a not too deep level, but to hopefully give you some intuition how they work. That's the plan. And again, if you have need for coffee or if you have, if you have questions as before, please interrupt. Okay, so we are talking now about solving these kind of problems. Okay, and of course, before we've seen them, they just had meanings. Now they're just like we have equality constraints, we have inequality constraints, you have an objective function in an n-dimensional space. And we assume that these functions are twice like differentiable and nice. We have second derivatives and so on. Okay, and of course, a point that satisfies all constraints is called feasible. Okay. And I'm now just here say omega, that's the set of all feasible points. It shows up on the next slide. And that's called a nonlinear program. Yeah. Okay, so I already said, and I'm pretty sure you know, there are different kinds of minimizers. One is the one you would really like to have, which is saying among all the feasible points, I want the one for which there's no better objective function. Right, that's the global minimum. Okay, and everybody wants this. Okay, that's right. Ideally, that's what you want. So if you have a function like this, oh, I could draw. If you have a function like this, you want to have the lower one or not this one. But as I said before, depending on the size of the problem, what kind of problems you have, that's really hard. So instead, what we usually contend with is finding a local minimizer so that it's a feasible point, so that for all points that are not too far away, so that in a neighborhood, there's no better point. Okay, so if I have this here, in this interval here, there's no better point. I mean, I'm pretty sure you've seen this before. Okay, so and we will discuss methods to try to find these local minimizers. Okay, one nice set of problems is when you have convexity, and instead of having the condition there, if you have a function where when you draw a straight line between 2 points on the graph, it's always above, that's a convex function. That the nice thing is if you have a convex function and you try to find, and you find the local minimizer, you always guarantee to find the global. That is also the global minimizer. And similar, like if you're,
Good ones.
Oh, okay. And then if your feasible, wow, if your feasible set is convex, okay. If your feasible set is convex, meaning if among two. I didn't even hear it. The absence now. Okay, so we call something a convex set if the line between 2 points is also in the set. And if you have a set that's not convex, for example, looks like this. Okay, and let's say you want to basically minimize x, whatever is in this direction, then having a non-convex set can create here a local minimizer. Now, because if you wanted to go further in the right direction, you would become infeasible and so on. So that's a local minimizer, that's a global minimizer. So non-convexity is the thing that causes you to have a local minimizer. So in quite some cases, you can formulate problems so that they're convex, or you can have approximations of the problem so that they're convex. So it's all great, but I'm assuming here that we don't have that. Okay, so if the function and the feasible set are convex, then every local minimizer is a global minimizer. Okay. Now I'm trying to show you the optimality conditions on a bunch of pictures. So let's say we have a simple optimization problem where green is this feasible set. So everything on green is feasible. And then here I have the gradient of the function. Okay, so the gradient is the direction in which the function increases most. So the negative gradient is the direction in which the function decreases most. So now let's assume that's maybe a linear function. So the negative gradient always goes into this direction. Okay. Where is the minimum in this picture? So if I have a function where the gradient is this way, so if I go in this direction, I can always further decrease. Where? There? Why?
Because you have to be on the green line so that the constraint is respected, and if you go higher, you minimize fx. So the higher you go, the lower the value of fx because of the gradient. So you have to be on the green line on the highest spot.
Yeah, and if you have, what would happen if the arrow would go this way?
Well, it would be a little bit to the right.
There or something,
Yeah.
right? Right? Because if you know, let's look at a different point like this one here. Okay, so here we have the gradient of the constraint. So if you have the feasible set, the gradient is always orthogonal to that. Okay, and if you move orthogonal to the gradient, you're not changing the function. At least up to first order, you're not changing the function. So that means if you are feasible here, the thing has a value of 0. If you go orthogonal to that, you stay feasible. Okay, so basically that means the linearize moving in this direction here still keeps me feasible. Okay, this here is the negative gradient. Okay, and I know if I go in a direction that is orthogonal, I'm not changing the function. But if I go in a direction that has less than 90 degrees, like this one here, for the to the negative gradient, I will decrease the function. So in this picture here, if I stay on this dotted line, I'm not changing the constraint violation, but I can decrease the objective function. So that's not optimal. So I think what you were looking for, is this point here, where you basically say, okay, so I'm at the point here where if I'm staying feasible, okay, there's no direction in which I get better if I look at the gradient, right? Here, the projection gave me a part in which I could move. Here, the projection is 0, it's not there, right? So this here is a point that is optimal, okay? So we can write this mathematically by saying, okay, so here, the negative gradient has to be a multiple of the gradient of the constraints. So that's the optimality condition here. Okay, if I have a one-dimensional problem, this is how I could look for a solution to that problem. Okay, now often you might have, of course, you have not just one constraint, but several constraints, but that just generalizes. So instead of saying that the negative gradient is just a multiple of that one gradient, you say the negative gradient is equal to a multiple of like a linear combination of all the gradients. Okay. Right, so mathematically can prove if you have a minimizer, these multipliers exist. Okay, and to write it in the short form, so I denoted this as the gradient of a function. If I here have a vector valued function, right, this can be have many m constraints, then this is just basically putting all the gradients in the column, so that's just the same way. Okay. All right, so what about inequality constraints? Can you give me the optimal solution here? Oh, I should say what that is. So on the green thing is all feasible. Then let's say I have an inequality constraint where the gradient is pointing this way. So in this way, the constraint violation would get worse. It's less or equal to 0, so it gets worse. So here, this constraint says it's satisfied, this is equal to 0 on the big black line. But then if I go below, it becomes bigger than 0, so it's infeasible. So the feasible set is what? It's everything that's above and is on the green line. So this is the feasible set. So where's the optimal solution here? I know a trick question. Yes.
Well, the gradient of CE and minus gradient of F look parallel near that point.
Here.
So at that point, it's either a minimum or a maximum. And if you follow that line to the left where it crosses again, it's also like if you
This
follow
one or this one?
the green arrow until
Yeah.
cross here also, they're also parallel, so it means it's also either a minimum or a maximum. But looking at the direction of the F gradient, you can see that the left point is a maximum and the right point is a minimum.
Yeah. So yes. Well, you mean this point here, or somewhere else? But okay, let's do this one at a time. So yes, so this point here already kind of gave you what the optimum is, right? It's the same situation as before. I can write the equality constraint. So negative gradient is a multiple of the inequality constraint. The negative gradient is a multiple of the equality constraint gradient. There is an inequality constraint, but it doesn't matter whether this is here or not. It has nothing to do what happens locally here. And we talk about local minimizers, right? So whether the constraint is there or not doesn't matter, right? So I can just still bring this negative gradient in the same way into the picture here and say I'm multiplying this with some lambda multiplier, but it's 0. So if I have an inequality constraint that's not binding, not active, the same as before, I can write it, I can formally introduce it here, but I can just say this, that I just have a 0 multiplier. But here, I have another minimum. Okay, again, assume that this is negative gradient. Why? So, I have a dotted picture? No. So, in terms of the green equality constraint, if I stay like on this line here, okay, and I have the negative gradient here, it tells me if I would go in this direction on the green line, I would decrease the objective function. Okay, so it would get better. But the inequality constraint here prevents me from doing this, right? So if I look at this here, if I wanted to go, if I go in the direction that now makes the objective function this smaller, I start to violate the constraint. So this is not desirable. So if I want to stay feasible with respect to the green one, I cannot go up, I can only go down. Okay. But if I go down, I start to violate the constraint. Okay. And I can still now write the gradient, the negative gradient as a linear combination of these two constraint gradients, okay, by simply taking this part and this part. Okay. And the important thing that I have here is that in order to do this linear combination, I have a positive multiplier. This goes down in the same direction as this thing for the inequality constraint gradient. Okay. So if I summarize this back here, I again have this written as multiplier for the equality constraint gets me out all the way here, plus a positive multiple of the inequality constraint gradient that gets me down here. Okay. So this is a local minimum. If, however, I'm on this side here, what happens is, okay, staying here on this line keeps me feasible. Okay. This here tells me that because the projection of this negative gradient onto this tangent here would go up. So I can move up, so get a better value for the objective function. I can stay feasible with respect to equality constraints. Okay, so I can move up. And the gradient here is, and I release the inequality constraint. So that's good. So the difference in this situation here, okay, where I have to add a positive multiple of the inequality constraint gradient to this one is here, is that now I have to add a negative multiple of the inequality gradient. So that's the wrong way. Okay. So this here is an example of not a local minimizer. So the difference between this one is I can write the gradient, negative gradient of the constraints as a linear combination. I can write the negative gradient of the objective function as a linear combination of my constraints. And the important thing is that the multiplier for the inequality constraint is positive. That's a local minimizer. The other situation here is same thing, but the multiplier would have the wrong sign. So that is not a local minimizer. The summary, okay? So basically, what is important is that you can somehow write the projection of the tangent, so that you can write the negative gradient as a linear combination of the constraint gradients. If I project this to the other side, it's this one here. So in other words, I can find these multipliers to write it down like this. Okay, and what that basically means is there's no decrease in the objective function and stay feasible, right? We want to make sure that these multipliers have the right sign. Because what it means here is that if I release the constraint, I would actually make the objective function better. Okay, so the multipliers have to be greater or equal to 0. And then I also have a condition that basically says an inequality constraint, it's present here, but if it's not active, it cannot play a role. So if this is not active, I'm away from it, the multiplier has to be 0. What does active mean? Meaning binding. The constraint would have the value 0. So here Ci of x is equal to 0. Okay. And so the way I can combine this is to say here, this combination tells me that only constraints that are active can play a role. So if I have a constraint that is not active, is above, if I'm here, okay, here this value of this constraint is not 0, it's something else. If I plug this in here, then this is non-zero. So the lambda has to be equal to 0. So if I have a non-active constraint, non-zero value, the lambda has to be 0. The constraint cannot participate. If I have an active constraint, then this lambda is allowed to take non-negative values. Okay. And that's called a complementarity condition. So at least one of these values has to be 0. And I can combine this all then in a nice theorem that says basically, if I have a local minimizer and the functions are continuously differentiable and a condition that I'm going to talk about again in a bit. If these hold, then it's guaranteed that I can find these multipliers to make this linear combination. Okay, I can find those. Of course, the point has to be feasible. It's a local minimizer. It has to be feasible. These inequality constraint multipliers have to have the right direction. And I have to make sure here with this complementarity constraint that only inequality constraints can matter if your point is at the inequality constraint. Okay, so this is a necessary condition which tells you if I have a local minimizer, these multipliers exist. Okay, and so this is then what the algorithms do. The algorithms say, okay, so I have these nice conditions. If I want to find a local minimizer, I know this local minimizer has to satisfy the condition. So I'm going to try to find an x. I try to find a lambda e and a lambda I so that all of this holds. And that's basically what the algorithm will produce. The important thing now to take away from this is these are mathematical conditions that have to be satisfied at a local minimizer. So that is why algorithms try to find these kind of points. Okay? Now, they're only necessary condition. If I have a point that satisfies it, so if I have an x where I can find lambdas where all this is true, it doesn't have to be a minimizer. And of course, you know from unconstrained optimization, what does that mean? Unconstrained optimization, there just are no gradients for constraints here. It just says that the gradient of f has to equal to 0. Of course, we know, right? So a local minimizer without constraints, the gradient has to be 0, but it could be a minimizer or a maximizer. So something else would have to be looked at to figure out what it actually is. But these algorithms, basically the goal is only to find points that satisfy these conditions. There's no guarantee that they actually find a local minimizer. There are mechanisms in there that try to make sure that they don't get there, but there's no guarantee. Okay? Okay, so one thing here that is important is this is not always true. It's not always true that I have a minimizer and can find these lambdas. Okay, here's an example. So I have the objective is to minimize x1. the constraint is saying I have to be below this the x to the 3 function. Okay, that's what this says. And this here says that I have to be on the positive side here, on this positive part of the axis. So the feasible set is in between here. Where's the optimum? That's maybe I get people waking up again. Where's the optimum here?
The 0, point.
Yes, exactly. Right, that's the smallest I can make the x1, okay, and otherwise I get infeasible. So what are the multipliers here? So how can what's the gradient of I have here the gradients of the constraint. So that's the gradient of the inequality constraint. That's the gradient of the equality constraint. They're orthogonal, right, to the tangent and so on. So what are the multipliers here, right? My theorem said that I should, because it's a local minimizer, I should find a multiplier for the two gradients and get them here.
They don't exist.
They don't exist, right? Weird. The theorem told me they exist, but they don't exist. And that is because there's this one assumption here that isn't satisfied. And that means that a constraint qualification has to satisfy. It's a weird word, but basically what a constraint qualification is another assumption that makes sure these multipliers have to exist. Do you know why that is wrong? What goes wrong here?
Well, I can express the negative gradient of x as a linear combination of two expressions.
Right. Exactly. So no multipliers exist. So a constraint qualification doesn't hold here. But so what that means is these algorithms that are looking for these kind of stationary points, these KKT points that satisfy the condition on the previous slide, they wouldn't be able to solve this problem. Okay. So that's one thing I just want to make sure that's also understood. We have these algorithms that are looking for these points, but there are situations where just by the nature of maybe the feasible set or whatever, it just isn't possible to use these algorithms, but that's rare. And it turns out you can make little tricks. So it turns out if you actually relax this a little bit, you think about this just a tiny bit, the gradient for the inequality constraint tilts a bit. And then you can actually express the negative gradient. It's just with huge multipliers. But this is how some of the methods get around with it. They relax it and so on. But in terms from a theory, it's, I think, important to know that this is not always true. So the constraint codification is simply a condition that makes sure these exist. And so if these multipliers do not exist, the algorithms that look for these KKT points that we saw there might fail, okay? One constraint qualification is if all your constraints are linear, the multipliers always need to exist. So if you have an LP, linear program, this weird thing can't happen. You always find multipliers. Or if, this was this one here, or if all the constraint gradients are linearly independent, it can't happen. Well, here the two constraint gradients are linearly dependent, pointing in the same direction, right? So it can. That is violated here. And there's another one. Okay. So the bottom line is we have these optimality conditions. So our algorithm tried to find points that satisfy those. Okay. There are situations just by the nature of the problem where that's not possible. So there's sometimes workarounds and so on. But that's the situation we're in. Okay. Okay, I'm skipping the next few slides. I'm just telling you now on a high level, this was a necessary condition. So also maximizers might satisfy these conditions, right? As in, if you're unconstrained optimization, how can you figure out if you have a minimizer or maximizer? You look at the second derivatives. If the second derivative is positive, it's a minimizer. If it's negative, it's a maximizer. Now, second derivatives in higher dimensions are expressed by the Hessian matrix. This has all the combinations of the partial derivatives. And you just have to look at, is the Hessian matrix, does it have the right curvature? Is it positive definite in the right null space or so? If you want, you can look at the slides then later, but they're basically conditions that tell you if in the null space of the constraints, the matrix here, of the Hessian matrix, which of the Lagrangian function, which combines the Hessian matrices of the objective and the constraints. If that is positive definite, positive semi-definite, then if it's positive definite, then it must be a local minimizer. Okay. if you only know it's positive semi-definite, it's not a guarantee, because there might also be situations where that's not true. Anyway. Okay, so that was my attempt to introduce the optimality condition. Now that we believe them, let's work with them and design an algorithm. Okay. So integer point methods, they're trying to solve these kind of problems. Before we saw inequality constraints, but of course you can, if you have an inequality constraint, you can just reformulate it and with slack variables, right? So this is not so basically you can formulate every problem kind of in that kind of form, and that just makes it easier to present, okay? And I also assume here that whatever bounds I have, they're just non-negativity constraints, and all variables have this just to make the presentation easier. Okay, so now we want to solve this. We have non-inequality constraint and just non-negativity bound constraints. Okay. This is a hard problem so one way of trying to solve this is to guess which of the constraints are active. Okay? Which of the constraints are satisfied with equality and which are not. Okay? And there are algorithms that do that. And if you have a large problem, though, there are many combinations. X variable x1 and x2 and x5 could be active, or x2 and x3 and x10 or whatever. So there are tons of combinations, and these algorithms are clever. But in the worst case, they really have to look for a lot of combinations of these sets of constraints that could be active. Okay. So this is how, so because then we wanted to solve problems that are bigger than this, another idea came about, and that is to say, instead of keeping these inequality constraints here, I replace them by this funny term up here. This is it's called the barrier term. Think about what happens. So x equal to 0 is the bound of my constraint. Okay. So what happens to this thing? If x goes to 0, the logarithm goes to minus infinity. Okay. If I now take the negative of this, it goes to infinity. Okay. So what I have is, I have a barrier that goes really big, goes to infinity if I get close to my bound. So it pushes me away. Okay. So if I have, here's a simple example where I basically have a problem where I have x has to be between 0 and 1. Okay. And let's my objective function here, I didn't write it down, it's just minimize x. Okay. So if I have, I have this parameter here that tells me how important is this barrier parameter. So if I give it the value of 10, then this is how this function looks like. If I go to 0, one of the bounds, then this term here blows up. Log x goes to minus infinity, so this becomes huge. And on the other side, I have the same thing. So now, if I look at this problem here, where's the optimal solution? Well, it's not at the boundary, it's somewhere in the middle. Okay. But I'm now solving a different problem where I have really introduced this term in the objective function that messes up what my original problem is. So I don't want this. So instead, what I say now is, okay, what happens if I actually reduce this barrier parameter? So if I make it 1, then I still see, the barrier blowing up at the side, but I recover already a little bit that my function actually decreases when I go to 0. So the true objective function would go like this. Okay. If I reduce the barrier even more, this is how it looks like, and so on. Okay, until it's like really down here. Okay. So this suggests an idea how to solve these problems. Okay. If I look at this problem here, there's no more inequality constraint, so no combinatorial thing. If I solve this, I have a local minimizer here. If I decrease my barrier parameter, I have a local minimizer here, and so on. And because I make this smaller, the effect of the barrier goes away. And as I solve the sequence of these problems, I'm recovering the solution of the problem that I really wanted to solve. Okay, so a barrier algorithm works like this then. I'm saying, okay, I have some starting point. I have some initial value of my barrier parameter. Okay, and then I just solve this barrier problem. Okay, for maybe mu equal to 10. I solve this. This is a nice problem. It has only equality constraints, so nothing complicated about selecting an active set. Okay, and I solve this. Of course, if I want to solve this problem here by solving a sequence of these problems, like having a minimizer here, having a minimizer here, having a minimizer here, I don't need to solve each of these barrier problems to high accuracy. If I if I want to use this here as a starting point to go to the next one, I don't need to have the value of the minimizer here very accurately. So what I'm trying to say then here is that I can solve the barrier problem here only to relax tolerance, save work, and then I can decrease my barrier parameter, tighten the tolerance, and then keep the whole thing in a loop and decrease the barrier parameter. So the algorithm that I want to describe follows this principle, where you took away the complication of a combinatorial search for active, what constraints are active, by a barrier term that you add to your objective function. You recover the solution of the problem that you wanted to solve by solving a sequence of these barrier problems where you decrease the barrier parameter in every iteration. So now the question is, well, once I fix mu, I still have a nonlinear optimization problem. I have a nonlinear objective function here. I have nonlinear constraints here, right? So now the question is, how do I solve this barrier problem once I fix mu? Okay. Then I solve it to, right? So that's the question we now have to answer. So here it is. And these are the optimality conditions I tried to introduce earlier, right? What do we have here? So we have here the gradient of this objective function, and here's the gradient of the constraints. So what's the gradient of this? Well, it's the gradient of this part here, and then the first derivative of this. Okay. So the derivative of log is 1 over x, right? So this is one way of saying I have a matrix here. I have a vector here that has minus mu times 1 over x1, 1 over x2, and so on. Okay, capital X here is simply a diagonal matrix that has x1, x2, up to xn on the diagonal. If I take the inverse, it's only this. It's 1 over this. Okay, E is the vector of all ones. All ones. So when I multiply these two things, it just is 1 over x1, 1 over x2, 1 over x3, and so on. So indeed, this here is just it's a compact way of writing the gradient of this barrier function. Okay. Okay, so fine. These are the optimality conditions. As I told you, we are looking for x and lambda that satisfy this. Okay, so it's a nonlinear system of equations. We know how we can solve nonlinear system of equations. Have an idea? If you have a nonlinear system of equations. Yay! Well, we talked about this before. Yes, exactly. So Newton's method is a great method for solving nonlinear system of equations. I have as many equality constraints here as I have variables, and as many as many conditions here as I have variables. I have many conditions here if I have constraints. How many variables do I have? As many as the variables, and as many have multipliers. So this is it's a quadratic nonlinear system of equations. So we can apply Newton's method. Newton's method means I look at this as a function of x and lambda. I take the first derivative. That happens to look like this. Okay. Then I get the displacement here. That's the step that I will take. And then this is just negative. That's the negative, that's this system here, evaluated at a current iterate on the right-hand side. This is just standard Newton's method. Okay. And for, to making things short, whenever I have an iterate xk, I just say lambda ck, nabla ck is just the gradient of c evaluated at that point. So in my Newton's method, I have iterates for xk and iterates for lambda k. I set up this linear system. I solve it. I take the step, go on, and so on. And the nice thing about Newton's method is that eventually converges really fast. Okay, so that's why Newton's method is a good way of doing this. But I already said here, here's a problem. Here, we have 1 over x standing here. Here, if you take the second derivative of this thing, is 1 over x squared. So here, this is why there is a 1 over x squared, right? If you take the second inverse of this, or x to the minus 2, then you would have squares here. So as I'm solving the problem, my optimal solution might lie at 0, right? So what happens then? Well, then these numbers really become large and essentially go to infinity. And the matrix isn't really defined at the solution, right? Because there's like you cannot take 1 over 0, right? So mathematically, you could still do this, but you're fighting with ill conditioning of this matrix. And there are other things where just it leads to convergence problem, makes things converge slower in the end, and so on. So that is not really the formulation we would like to use. Okay. This is at the beginning how people, when they started working with barrier methods, what they did, and it didn't work as well. But we can do a trick. And that is, so this is just copied again, the optimality conditions from the previous slide. I don't like this term here. I don't like this 1 over x part. So what I can do is I can just introduce a new variable that just is this thing. Okay, so now instead of this here, I have a z here. Okay. Okay, so I introduce a new variable that just I plug in here, replaces this. There's no more 1 over x. But I now still need to make sure that the variable z will take the right value, right? So I want that z, this is a mess now. So that z is equal to mu times 1 over x. That's what the definition is that I wrote down. So I can simply multiply this by x. And I have that the product of the two has to be equal to mu. And one compact way of writing this is just this. Okay. So this here is equivalent to this one here, having introduced a new variable. And it's a dual variable. If you look at this system here now, there's no more division, nothing 1 over anything. So as we go to the optimal solution, there's nothing weird that happens anymore. So it's a much nicer system that we can solve. And now we can apply Newton's method to this. Okay. And now, again, there's nothing here that also in the derivative matrix here, where we see anything nasty. The x just now shows up here as a regular, like times x as opposed to times 1 over x, and so on. So nothing is nasty as mu goes to 0. Okay. So, and this is in principle what the algorithm does. You pick a value of your barrier parameter. Now you need to solve this optimization problem for fixed mu. Okay, it's an equality constraint problem up to a certain accuracy. And you can do this with Newton's method here. Okay, these are equivalent, so you have this extra z variable, but that's fine. You look for your x and your lambda that you need. And then once you solve this sufficiently, you decrease your mu and you keep going. Okay. Now we know that Newton's method doesn't necessarily converge. Newton's method, if you know that you're close to the solution, Newton's method will converge to the solution or the root of the nonlinear system quickly. But if you're far away, you might take a bad step, or you might cycle or something like this. So you have to be a bit careful. Okay. So you cannot really necessarily take the Newton step itself. So you have to take a step size here. So you have 3 variables here. You have your x and your lambda and your z. And we decided to take the same step size for the x and lambda variables that showed up before I introduced this, and then a step size here for the z variables. Okay. Now 2 things matter here. So my x cannot be negative, because then I would have to take the logarithm of a negative number. So I have to make sure that in every iteration, none of the x's becomes negative. And I also know that the optimal solution here, the z, defined this way, has to be positive. Okay, so I make sure that while I'm iterating, that all my x's, all my z's are always positive. If you have the Newton step that doesn't know about this, it might really leave this. So you have to make sure you're introducing a step. And for this, what we typically use is called the fraction to the boundary rule. Essentially, what this says is, here, this is my current iterate. Okay, this is the step that I take. If alpha is equal to 1, I would take the full Newton step. But okay, let's choose something smaller. Now, what's on the right-hand side here? So if tau here is a number like this, then this would be 0.01. Okay, on the right-hand side, if x has the value 1, this thing on the other side has the value 0.01. Okay, so allowing myself to go down to this level means I'm allowing myself to go up to 1% closer to the boundary than I was before. Okay, so it's a fraction to the boundary. I'm only now allowed to go 1%, up to 1% close to the boundary. Why do I do this? I could also say, well, just go arbitrarily close as long as it's not 0, but that's not a good idea because then your variable blows up and also prevents you from converting quickly at the end. So you need to make sure greater than 0 is not enough. You just cannot become, you still have to have a certain, you have to keep a certain distance. And even though that makes sure you're not getting close in each iteration, at some point, as you iterate, you know, because of the barrier, it will actually go away. So you will not, you cannot converge to x equal to 0 after many Newton steps. Okay, so this is what we call the fraction to the boundary rule, and we're making sure that we take this step both in x and in z. Okay, so if you compute this for z, this is the iterate that we take. That's the step that we take. But now something else can go wrong, and that is simply we have nonlinear functions, right? So if you have, if you take a step, there's no guarantee that you're actually making a step towards the minimum. You might get too far, and the objective function goes up again, or something like that can happen. Okay. So in addition, we're doing we do a line search, which means is we first try what the maximum step size is that we could choose. So j equal to 1 would mean we choose an alpha that's equal to the maximum step. Then I look at, well, this would be my trial step. Maybe I want this as my next iterate, maybe not. How do I find out? Well, let's actually look what's going on with the functions. They're nonlinear. I have no idea. I cannot really predict what they're doing. I really have to evaluate them. So I evaluate them here. And then I have to decide whether I'm making enough progress, whatever that means. So if I wouldn't have constraints and I want to minimize a function, progress means I decrease the objective function. Simple, right? But if I have constraints, maybe I have to increase the objective function in order to become less infeasible. So figuring out when you have constraints, what is acceptable or not is more complicated. Okay. But this now basically is the main algorithm. What I do is in each iteration, okay, at an iterate x, I compute the Newton step. Okay. I compute the largest step size I can take. And then on top of this, I might have reduced the step size for my primal variable, for these x variables, to make sure I'm not just going up into the wilderness and I'm not bouncing around. Okay. So the next few slides are about deciding, you know, am I making enough progress so eventually I will converge or not? And there are different ways. So one way is to say, I just make, well, there are different ways of doing this. I'm presenting you one way of doing this. Okay. And this is what's called the filter method. Okay. It was invented by Roger Fletcher around a little bit before 2000 and so on. And that's the method that also we ended up using in this. Basically, the algorithm I'm describing here is the one that's implemented in IPOpt. Okay. There are other interior point algorithms that now do not use a filter, you do something else. But to be specific about one method, I'm going to talk about this one. Okay. So if you have your optimization problem, you have an objective function and you have constraints. And there are two goals that you have, right? One, well, I want to make my objective as small as possible. It says minimize x, right? Minimize f of x. I want to make it as small as possible. But there's a competing thing, and that's the infeasibility, right? So if I say theta here is the norm of the constraint violation, I also want this to be 0, right? I want to minimize my f, and I want to minimize the constraint violation. And there can be conflicting goals, right? It's a bi-object optimization problem, but they can pull in different directions. And the idea then is to say, okay, if I have a trial point, okay, how do I decide whether it's good or not? And for this, we can look at this picture here. So here, basically, we have these two objectives. We have the constraint violation here. We have the objective function here. The set of fees, and then any point in x right? Any point in the real space can be just mapped here by evaluating what is the constraint violation here, what's the objective function value, and here it corresponds to a point in here. Okay, where are the feasible points? Where are the feasible points? Or where, if I have a feasible point, where would this show up here in this picture? Right? Feasible means theta is equal to 0. No constraint violation. No, it's an equality constraint. So, right, so you compute the norm of this. So 0 is theta equal to 0, the norm being equal to 0 is the only thing where feasible points, right? So this would mean any point that is mapped here in this graph onto this y-axis is feasible, okay? So among all the points that are mapped here, which one do I want? Well, the one with the smallest value of the objective function. So this here is the point that I would want. I want a point, an x star that is here, okay? That's where I want to go. But I might have an iterate now that's somewhere here, certain value of the constraint violation, certain value of the objective function, right? So when am I making enough progress? Well, the filter basically says, well, okay, if I improve one of those, so improve means less infeasibility this way, or improve means less smaller value for the objective function this way, just any point here is better, okay? It's clearly worse if make both worse, so then this is not okay. Okay. Now, when you talk about convergence and guarantee for convergence, you need to make sure that you're not only making progress, but enough progress. If you only, if you want to go down here, this is where your objective, where your minimum is, and you always decrease, but not enough, you get stuck. Okay. So that's why there's a margin around this that says, okay, this point here makes, you know, that is less infeasible, so it's good, but it's not enough less feasible, because I want to have always that there's at least a certain reduction in the infeasibility, certain percentage in the infeasibility to make sure that eventually I get to a feasible point. Okay, things can go wrong. What could go wrong? If I have an algorithm that says, okay, I have an iterate, I look at the infeasibility, the objective function, and as long as one of them gets better, I'm taking the step. And I do the same thing in the next iteration.
Make one better and the other worse, and for that.
Exactly. I could just I could keep jumping between these two. Okay. Newton, who knows what the Newton steps do, but this is what could happen. So I need to prevent this. So what Fletcher and Leifer said is, okay, let's just simply store these points in this two-dimensional picture in this that correspond to previous iterates. So if this is my current iterate and now I jumped here, then I store this one, okay, and I store this. So if I move from here and I go here, I store this one in the filter. They call the filter. And I make sure that I'm not only making enough progress with respect to the iterate where I am right now, but also with respect to everybody else. Okay, so I cannot cycle. I cannot keep going back. Okay, so the filter is basically trying to make sure that you do not cycle. Okay, and that's the basic idea. There are some subtleties that basically say, if I would do this all the time, I actually might box myself into a corner, and then I can't do this. I cannot progress. So it actually, for example, so this is the condition that says, so this here is basically telling you by how much the objective function would decrease for a certain step size for the step that I have. And if that is large compared to my current constraint violation, that means I'm kind of feasible, but the objective can really decrease. I should really now insist on making the objective function smaller. So if I have this kind of switching condition, I say, I don't care what happens to the constraint violation. It doesn't matter if I make this better. I really want to make sure that my objective function is better. So that the new objective function value is less than this, again, with some kind of margin. So that's here. Yeah. So that's a negative number. So the minus is a positive number, negative number. Okay. And so all these things then together, you can prove that that the algorithm that you have will converge to a stationary point. So a point that satisfies the optimality conditions. Again, that's no guarantee that's a minimizer, right? But the fact that we keep insisting on always having a decrease makes it much less likely that you're converging to a maximizer. I'm skipping here a lot of details, but I also wanted to kind of keep it on a not too somewhat higher level. Yeah. Okay.
I think you have a question.
Yes.
Yeah.
Sorry.
I think I get the concept of the filter, but just before, like, you express the solution as a bi-objective simulation. Can you explain what is what are the two objectives and what is the theta on the?
Oh, sorry. So the theta I wrote down here. Sorry if I didn't point that out today. So theta is just the norm of the constraint. So you want the constraint function to be equal to 0.
Mhm.
So the norm of it has to be 0.
So it becomes your second objective.
Yes.
in your- okay.
Sorry if that wasn't clear. Sorry. Yeah. So you want to minimize the objective, but you also want to minimize the norm of the constraints, the constraint violation.
Okay, and what did you draw, like the L shape on the line?
So thanks for asking this. That probably means you were the only one who didn't understand that. Okay. So so what I drew here is basically saying in my X case, it's in the n-dimensional space, but it has a certain value of the constraint violation, theta, and a certain value of the objective function. So in this plot, it's that point here. Okay. And now I'm saying here that what points will I accept? I'm not going to accept anything that makes both worse. So things that make both worse would be in this quadrant up there, right? So if I have something here, it means I decrease the constraint violation. If I have something down here, it means I decrease the objective function. Both good, right? So in principle, anything here seems good, and I would take that step. Okay.
And are you sure that those two are not related to each other?
So the way this, I have my iterates, right? And I take a step, and they are, of course, they're related, right? So this point, and I don't know really what happens. It depends on where you are in the space, depends on the functions, right? So it could happen that you just take this point over here. But what you can guarantee is that if you make your step size small enough, you will actually decrease the constraint violation and end up on that side. So once you make your step size small enough, you will find an acceptable point. Thank you. Yes.
I'm not sure I understood why we decided to add the logs a few slides ago. I understood it was because we wanted to it was hard to know which constraints were violated. That's what I understood.
Yeah. Okay. Thank you for asking, because it means I should backpedal here.
But maybe I didn't.
No. I don't know. I think it's good you're asking.
Because I was thinking it should be easy to know which constraint is violated. I can just compute it. Like
so you want to solve this problem.
Yeah.
Right? So if you have only an equality constraint problem, like basically what we have here, okay, these are the optimality conditions. Okay, there are no inequality constraints, just that.
Yeah.
So you can just use Newton's method to solve this. Okay, if you look at the original constraint optimality conditions, okay, here, this is, then you have this additional stuff here where you need to make sure you don't have, they have this weird complementarity thing here. So you have to worry about these things. That's much more complicated than just solving a nonlinear system of equations.
Sure.
Right? So if you keep your inequality constraints, you would have to deal with that.
Yeah.
And one way of dealing with this is to just guess which things should be 0, which of the constraints are active. Okay, so it have to be satisfied with 0. And then basically, yeah, and then you have the corresponding lambdas. and try to solve that. Again, with some kind of Newton's method.
Okay.
And then the thing is, guessing what is right is hard, specifically in higher dimensions.
Okay, because you don't know the solution and then you want.
Yeah, exactly. Right, exactly. You're trying to find the solution. You don't know, is that where this constraint is active or not?
Okay.
Yeah.
Okay, I see.
And I mean, when I say guessing which constraints are active, it's not the algorithms that are doing this in an intelligent way. Okay, so and they work fine for small problems. These active set methods work really well, but when the problems become really large with millions of variables, they're totally useless because they do. So for linear programming, you have the simplex method. Okay, who knows what okay, in linear programming, you have the simplex. Didn't want to put you on the spot. On the linear programming, you have the simplex method, which is trying to figure out what the optimal basis is. It tries to figure out what are the active bounds, okay? They work fine up to a certain size, but for bigger ones, you then need these inter-point methods to really solve the large problems. And it's the same situation here. Just a trade-off between what is big and when do you have to switch to the inter-point method is much smaller when you have a nonlinear problem. Yeah. Yes. Also, there are many different levels to answer this from. But here, okay, so if I just look at it, oops, man, this thing is not my friend today here. It's like going all over the place. So this here, I just take this problem. I take the optimality conditions, which means I have to take the gradient of this thing. I have a 1 over x here, okay? And as mu goes to 0, like in this picture here, the minimizer is here, then I make mu smaller, goes here, mu smaller. So I'm actually going to the optimal solution, which is at 0. So I'm going to 0. And then this thing here will go to 1 over 0, which is bad, right? It diverges. So you don't want this, right? And the way to get rid of this, that's one way of explaining this approach, is to say, okay, I don't like this. I just make a new variable here, z, which when I plug it in here, just becomes really benign. It's just minus z. But I need to capture this relationship between x and the new z that I introduced, right? So what is written here is z is equal to mu times x to the minus 1, which is just 1 over x. And I multiply this to the other side, and it's just x times z is equal to mu. And I wrote, this is now expressed here. This x times z is equal to mu. And the e just means that's valid for each of the components of the vectors. Does that answer your question? So there is no more 1 over x. This is all nice now. Okay, so optimization algorithms shouldn't be problems. Optimization algorithms for nonlinear programming are typically really trying to find solution like x's and lambdas and so on that satisfy the optimality conditions. Okay, that means they're not necessarily, you don't have a guarantee they go to a minimum. Okay, you would have to look at second derivatives and use second derivatives in the algorithm to guarantee that. It makes the whole thing more messy. It's still possible, but because we have this like steering us towards a good solution and a minimizer, in practice is actually pretty rare. Well, okay. In practice, you're often usually really lucky to get the right solution. And as I told you in these power flow problems, you basically got the global solution. So in many cases, you can prove that these find a global solution. If they don't, then you're still pretty close by. So if you have a problem, if you want a global solution, your problem is not nicely convex, it's much more complicated because then you have functions that look like this. And so if you think about it, finding a local optimum just means I'm looking for something close by, okay? And what did we do here when we looked at the gradient and so on? We're looking at Taylor's approximation. So if you're at an iterate, you can locally predict, because you look at the gradient and so on, you can predict what the function does. Okay, and that's why it means you can, okay, I'm always making sure if a step is small enough, I'm making progress and eventually I'll converge. But if you want to solve a global problem, you need to know everything. You need to the function everywhere, right? So that's why these algorithms usually have to look at the specific functions. Am I looking at sine function? Am I looking at logarithm or whatever? And what they do is they basically put the search space into pieces, like a branch and bound algorithm for binary problems, right? Or integer problems. And then separate the search space into pieces and says, okay, so here I can approximate my nonlinear function by convex function. I can solve this problem here. I can solve it here. As in branch and bound for nonlinear for integer programming, you can then fathom certain things and so on. If you understand what I'm saying, good. If you don't, that's okay. But basically, what this means is that solving a problem with 1,000 dimensions or so is really, really hard if you want to find the global optimum. Okay, so it's impractical for large instances. And that's okay. So into your point methods, they do avoid having to explicitly identify the active constraints. There's different software. So I talked about IPOpt, that's open source. Nitro is a commercial solver. And so my job at Gurobi now is to also get a nonlinear optimization solver in there. And there are others, I guess, yeah. And I think that's that part. Any more questions? Yes.
Just a question, is this actually related to how you solve the problem of the challenge one?
Yes, so we used, correct. So we used IPOpt.
And did you try different algorithms than the barrier one? Did you try another one?
Like what? I mean, so we use IPOpt because I just happen to know it really well, right? Well, I mean, so Elizabeth Wong, one of our collaborators, she worked on SNOpt, and SNOpt is an SQP algorithm, if you know what that is. It's an active set algorithm that tries to find the active set. No chance. These problems are just way too big. So we tried that one, that didn't work.
So it was more of an idea of the scale and the dimension of the problem. It's going to be addressed through the barrier.
Yes, I mean, yeah.
Okay. So because you could also think of ways of reducing the dimension of the problem, and like you talked about domain knowledge, and you spoke about the
yeah, it's hard. I mean domain, not like domain like area, right?
Yeah,
like,
but also in the way you explain how you attack the challenge, you focus a lot on contingencies and the link between the contingencies, the generator. But then in that problem, you also have all those piecewise linear functions of the cost of the generators. Maybe some of them are irrelevant, like there's maybe some work that you can approach to sort of cast out.
But trying to do all this
Yeah.
and trying to guess that would be much more effort than just running this algorithm that it doesn't really, I mean, the cost, I don't know how it scales, but the cost is like a little more than linear or so. Well, and the size, not even quadratic, so it's okay to have a somewhat bigger problem. Linear is wrong, but it's not quite quadratic, and certainly not cubic, because we're using sparse matrices. Yeah. Okay, so this is more about like a recent research project. So we had like Go competition application, now kind of introduce an algorithm. That's something else. I'm trying not to rush. Instead, I skip stuff. So I hope I'm not skipping stuff that makes it completely intelligible, but okay. All right, so this is again about decomposition algorithms, and you will see two-stage problems, what that means. I want to say that, so this is collaborators from that project. So these were, he's still a PhD student now. Those two students have graduated. Amin is my colleague from Northwestern, and then these are collaborators from Los Alamos National Lab. So those are people that really work on power systems. They have the that data. They had the domain knowledge. Okay. All right, so this is a decomposition algorithm based on barrier smoothing. Having just given you that lecture before helps to set that up. You will see one thing I said is convex problems are nice because they have only one local solution, which happens to be a global solution. In this setting here, usually people assume that this second stage problem is convex. We do not. So what are the problems that you have with this? And I have some numerical results. So the application is actually decomposition of networks, but now different. Now we're saying we have our transmission and distribution systems. Okay, and our decomposition is kind of the transmission system as the master problem, the big problem, and then having distribution systems that are connected to it. And again, don't ask me too much questions about distribution systems details. I'm not the power person, but I hope that whatever questions you have, I can answer. All right, so let's say totally stylized, we have here our network again. Again, our variables are the active, reactive flow, power voltage, phase angles, and so on. And we could just write the whole network as one big problem, right? Then we have, of course, these, we have, what's it called again? The connecting buses, substations or so, right? So they are there, they just one node of the whole thing. We have, so in our presentation, we have one phase here, but we have three phase representations of the distribution systems and so on. So we could just solve these as a big problem, but instead you want to decompose. Okay. And so if you think about it, what is happening at these substations or connecting buses? Well, okay, so they're described by basically having power injected into the distribution system, active and reactive power. There's a certain voltage level and there's a phase angle. Okay. And now we could think of it in this way. We could say we have our central network, our transmission system, which then sends into the distribution network power and also says what's the voltage. And then if you want to minimize costs, the distribution can then just say, okay, if I want to satisfy my demand, I have to generate that additional power. It costs me that much. Can send that information back to the transmission system in a sense. All of these networks can do it. And then the task of the transmission system is to say, okay, I want to minimize the overall cost. So one thing I didn't say is often distribution systems are passive. You put something in and so on. We're assuming here now we have active distribution systems. So we have internal power generation that costs something, and we want to minimize the cost of if you would look at the whole problem as a whole. Okay, so the decomposition is transmission system has its own cost. Okay, then the transmission system says, I'm giving you that much. Distribution system says, okay, thank you very much. In order to meet my demand, that much is more that I have to do. And then transmission system says, okay, thank you for letting us know. Now let me try to think how I can adjust my transmission system generation to minimize the overall cost. Does that make sense? Okay, and that's a two-stage problem. Because what you really have is, if you look about it this way here, right? You have an objective. So X here is our transmission system now. Here are all the variables for the transmission system. There's the cost for the transmission system, constraints for the transmission system. And then you have a contribution to the overall cost coming from the distribution systems. Okay, so there's this part here. Now, how does the distribution system figure out what its cost is? It says, well, okay, so you're telling me what you're giving me. You're giving me your X, your input. Okay. But given that, I still want to now minimize my power production. So I have to meet demand, so I have to do additional power production, but now let me do this in a minimal way. Okay. So the distribution system, once it knows what comes in, solves its own optimization problem. And that's the minimum cost now is that. And then that's added up, and you want to minimize the whole thing. Does that make sense? So those are known as two-stage optimization problems. Two-stage often also so this view of transmission and distribution system decomposition is not usually what you think of when you think of a two-stage problem. Two-stage problem is more like, okay, I have uncertainty. Okay, I have demand tomorrow. I have uncertainty. What's going to be? I don't know, newspapers. I don't know, something. And food. I'm sending that. but today I have to decide what I deliver. Okay, so that's my decision today, but I don't know what's uncertain tomorrow. So my first stage decision is what am I sending there today? Cost something. And then tomorrow, there are many different things that can happen. Okay, and then you can say, I'm taking the expectation of the cost by looking at a bunch of scenarios, taking the average, and then you would basically say, I have a bunch of scenarios. For each scenario, I compute now how much it would cost me to actually deliver what I have to deliver, given the uncertain demand. That gives me a certain cost, and I take the average over all the scenarios. Right. So in this setting here, the first is how much do I buy today to satisfy uncertain demand tomorrow, and then how much do you have to buy in addition tomorrow to do this. Okay. Okay. And yeah, okay. So, and there are many different ways of doing this. For linear instances where everything is linear, you have Bender's decomposition and all these nice things. We say no, okay, so we want to be, I don't know, complicated. So we have non-linear, non-convex constraints. Let's see what we can do. And we are saying, okay, so let's look. Here's a very simple instance. There's like the only objective function is really for the master problem is minimize the second stage function. So this is not there, no constraints, right? And let's say this is my problem. I want to minimize y subject to x1 and x2. These are my variables. And so on. And let's assume now that x1 and x2 is the input. So in this two-stage problem, right, there's the second stage optimization problem is characterized by the x, right? How much do I put in the distribution system? That's now input and fixed, okay? And then the decision is y. Same thing here. Let's assume in this simple example that here the first stage problem says, I'm giving you x and giving you y, giving you x1 and giving you x2. Now you minimize y. And then you tell me what is y. And I want to minimize whatever you tell me. Making sense? Okay. So here I basically drew what this function here is, the optimal objective function value as a function of x, which is the input. Okay, and it looks like this. So depending on which x I choose, you know, one of those constraints are binding. Okay, if my x1 is really large and those are not, then x1, y is equal to x1, and y is greater than everything else. So then I would basically be on this plane here. If I go have a different value of x, maybe another one of these planes, these inequalities becomes the active, it's the maximum, right, of things. And I'm on different of these planes, right? So this here is a picture of this function that I want to optimize. That's not a nice function because it's not differentiable, it has kinks. It actually has a kink whenever you transition from the activity of one constraint to another one. Okay. At this kink here, like this is where the activity switches between this and this. X1 becomes smaller, this becomes bigger, and the trait safe red. So because of these kinks, we wouldn't be able to use one of those nice solvers that use derivatives of fast and so on. So that's not good. So we are stubborn, we want to do that anyway. So what can we do to actually make this thing smooth? Okay. Well, and that's where the stuff comes in that I talked about before. So let's now think of this being our this is this problem here. Okay, the second stage problem. Okay. Gets its input to x. Then, given your x, you're solving the second stage problem, getting a y. And I introduce slack variables here because it makes it easier to write things down. And there could also be equality constraints, but it's easier this way. Okay. So what you really have is given an x, well, you can compute the optimal solution, and let's say it's y star and s star. Okay. And those, though, I mean, in this example specifically, the y is like this thing here, those are non-differentiable because each time you have to switch in activity and so on, you have a kink. They're not differentiable. That's not nice. So what do we do if we don't like inequality constraints about active stuff? We introduce a barrier, right? So this now is the same problem like this one here, but with our barrier introduced to handle the non-negativity constraints. Okay, seen this. And now you're saying, well, okay, given an x, this will converge to the true solution that I care about as mu goes to 0. Okay. All right. Fine. Okay, so again, I'm not really getting the solution that I want, okay, because I'm introducing this parameter, and again, I have something go to 0, but I'm getting something from this. And what I'm getting is that there's no more inequality constraint. There is no more this thing that would introduce the non-smoothness. Okay. And indeed, if I would write down these optimality conditions that we saw before, the primal, whatever we saw before, these are now the optimality conditions of this problem. Okay. The gradient of the objective function plus the linear combination of the inequality constraint, feasibility, and then this complementarity thing altogether. And I'm looking basically for given x, I'm looking for an optimal solution for this. So I'm looking for optimal values or values for y, s, and lambda that satisfy this relationship. Yeah. Now, this is just a nonlinear system of equations. You have Newton's method to solve this. Okay. But it also does something else. I have the implicit function theorem that now tells me, well, the root here of y, s, and lambda and so on, they depend on my x parameter, my input. And the implicit function theorem tells me, because there's no inequality constraint, this is differentiable, and I can compute the first and second derivatives. Okay. So actually, if I do the smoothing, here you see the same function that we saw before, and how this actually looks like if I solve this with different values of mu. You now see this is a smooth function. And I can actually use a gradient-based solver to do this, and I can compute first and second derivatives. Okay. So the idea of the algorithm is then this. You're choosing a starting point. So you're working here on, this is solving the master problem, first level problem, okay? I'm choosing an iterate. I'm choosing a first value of the smoothing parameter. And I say, okay, now let's solve this problem, okay? This first stage problem. I have too many steps here. Let's kind of solve this first stage problem. Okay. This is an iterative process. I could use active set method. In this case, actually, it's a good idea to do this, whatever. So I can use any optimization algorithm to solve this master problem. And the only way the second stage problem enters is with this function, the output function. Right? For given x, tell me subproblem, what is your function value? And actually also give me first and second derivatives. Okay. So now this problem, this solver that solves the first stage problem has all the information it needs to do a regular nice step. It has a smooth differentiable objective function, it has constraints and so on. And in each of its iteration, you can compute this. That also means for each of its iteration, you have to compute what this function is. In other words, you actually have to, for each iteration, xk is an input, you have to solve the subproblem. It's a cost that you have. But it does allow you to solve now a much smaller problem with a solver that can use second derivatives and converges fast, as opposed to having bundle methods or whatever. And then also, I mean, how do you solve this problem here? This is a barrier problem. We already have a solver. We have IPOpt or whatever. We already have everything implemented. It's all there. So the nice thing about this decomposition is that we have both. We don't have to write any more software. We can use what we have. Okay. All right. Okay. Any questions? Yes. Good.
The test line in the Wätcher command in Q, what is it? Which operator?
This one here?
Is the test line.
Sorry, which one?
This is like the
parentheses.
This?
No, in the parentheses of the value of the not here, was that true?
It's the round, the little round.
This, thank you. Oh, the operator, sorry, that was, yes. So it's a component-wise product. So if you think about, I wrote this before, it's just a different way of writing. Good question. Right, that I wrote this before, and I'm now also using lambda instead of z. Okay, sorry, I switched notation here. But what does this say? X times z is equal to mu in each component. And that's just another way of writing this. Okay, that's the same as this. Sorry, I kind of.
It's like simple.
Yeah, I switched notations here on you. So S is essentially what was X before, and lambda was essentially was Z before. Okay, it's still the same kind of relationship here, but it's now slacks. The X's don't have a bound, the S's do. So sorry. Okay.
I use this notation because that's the one I use.
So you're gonna use it, okay. So keep that in mind. Okay. I skipped this. Okay. But now, so what this project is about is, so we have, there's this smoothing thing, and you can say, okay, now how can I solve these problems? I can just use software that I have. I do my algorithm for the first stage, okay? In each iteration, it needs to know the value of this f. I call the other algorithm, it computes it, okay, for a fixed value of mu, and gives information back and so on. So you can do this. And if the second stage function, the second stage problem is convex, there's no ambiguity at all what this is, okay? That's just this one solution. So, but distribution systems are not convex. So what do you do? Well, okay, fine. So now we're saying our algorithm is only going to compute a local solution. What now? Because that makes things a little bit complicated. Here I have an example, okay, where this, won't even know what, it doesn't matter what f is. But this here is our first stage problem, and this is the second stage problem, specific second stage problem, function, okay? All right, so here I wrote the constraint. So this is whatever this is here. And the input, the first stage variable that's fed into the second stage problem is x. And it basically says this parabola has to be greater or equal to x. Okay, so here I have y, here I have x, and the question is, for which values of y is that true? Okay, so for a certain value of x, like this one here, well, this is true whenever this parabola thing is above the dotted line. So the y's that are feasible for this value of x are those and this. Yeah, this is where this formula is satisfied, and I have this bound here. Okay, I have now two parts of a feasible set, and for each part I want to minimize y, I have a different local solution, right, which I can plot here. So one is -1, and the other one is essentially 1 is here. And as I increase x, what happens? Okay, they shrink, right? So, okay, shrink means, objective function gets worse, so it goes up here. And then you come to this lucky point where, okay, so it's, this value here is whatever it is. And once I go above, it's gone. Okay, so I have two things here. For different values of x, I might have two different solutions, different local solutions. And in some, actually, kind of this trajectory disappears, right? And that's the problem. So if you're running a local optimization solver for this one, you don't know which one it returns to you. So we still want to have an algorithm that can deal with it. Okay, now a few minutes to explain to you what happens, hopefully. What do I need to do here? It's important. I think this is good enough. So what I'm plotting you here is the value. This is the value of the optimal y. Okay, and this here is the value of the recourse function. So I didn't. So this function here. So this is here. Now with so the difference between what I had here, these were the optimal values of y. But then if I actually look at what is the value of the second stage function, if I include the barrier, it actually they look like this. Okay. So in this trajectory path, the f function looks like this. If I follow this trajectory path, the f function looks like that. Okay. I know it skipped things, so but I hope that's still clear. So now this is what could happen. In this picture now, this is in the X space, in the space of the first stage variables. It says, okay, so here is the value of my, this is the value of my, this function here. Okay, is plotted here. This here is essentially this function here. But because they're different local minima, there's not just one plot, but there are two. Each of the plots corresponds to a different local minimum. So my first stage algorithm has this iterate, and then maybe it computes a step and gets it here. Now it says, okay, let's compute what the local solution is, and it gets this one. And now, because there's only one, and then it says, okay, am I making progress? So in this, there's no constraint. What does progress mean? Reducing the objective function. So it says, oh, no, this is worse, right? So no, you're not making progress. So what do? Take a shorter step. So now maybe you're taking this step. Okay. And you're telling, so you were at this iterate, and now you're giving this X to the subproblem solver, to the second stage solver. And there are two things it could converge to. Okay. In one case, you end up here, the unlucky one. Okay. And then again, it got worse. So you're gonna retract a step, you make it shorter. Again, you would reject this. Or maybe you're lucky and you get to this local solution, and that's a nice solution, and you go there and you take that step. Okay, then you had a successful step that goes forward. But let's say now you ended up here, and okay, so they have to just retract again. And in principle, the game could be happening, that each time could be happening, can keep happening, is that if you get a new iterate to the second stage solver, that always gets you the one on the wrong trajectory. That would mean every trial step is going to be rejected and you're going to stall. Okay, but here's the trick. What you do is, when you say you're solving the second stage optimization problem, it's an iterative algorithm that needs a starting point, right? And the best starting point is probably just to give, so this is then that's basically the y-axis if you want. The best starting point, simply, why don't I just pick the one that I had as the optimal solution before? So for this x, I had this as the optimal y, and I'm going here, let's just use this one as the optimal, at the starting point. If I'm here, their starting point is not close to any of them, might go anywhere. Oops. But here, if I now say I'm starting my second stage solver from here, Newton's method has this law of attraction. Once you're close enough, you will converge to whatever you're in the attractor of, right? So, and then basically that means if I use as a starting point the solution from the previous x, when I want to compute my new x, I'm gonna be attracted to the correct solution path that belongs to this local minimum. And that one is indeed the one that I want that goes downhill. Okay. Yes.
I guess the real problem is the first iteration. Issue ends up on the wrong trajectory.
Well, exactly. Yeah. Okay. So
you know that the second one exists.
Yeah, right. So everything is local. So I mean, we can do this, and because of this, you can prove that you kind of get to a local minimum. Okay, but it's a local, or it's always like KKT point anyway, right? But that's correct. So again, global solution versus not. I mean, if you happen to start here, and then you're unlucky because you end up as a different branch, you actually get really lucky because you go to this one and you switch to this one. That's great. So. Because that's where initialization. So, but yes, exactly. That's right. We implemented this nice software. I really owe my student to. We need to make this open source. We did solve. So here with our friends at Los Alamos, so we solved. I don't remember the details here, but so we had a transmission system that had so many buses, that many variables. We had 13 distribution systems, three-phase problems, three-phase formulations, that many buses. Artificial, of course, right? And so then again, you can decompose, right? Because for each, if you have different distribution networks, they all get their input at some point from the transmission system, I mean, mathematically input, and then you can solve these transmission system optimization problems independently in parallel. And then, so you can solve it. So for the master problem, it's better to use an active set method because they are better to warm start than interior point methods. And you're solving the sequence of these problems. For each mu, there's a different problem. So whoever understood what I was saying, I hope that made sense. And so it didn't take too many of these iterations, master problem iterations. And then and we needed 14 calls of the subproblem solver. Okay, so there were really only 26 iterations across all the different mu's. There were some iterations that weren't successful, so we needed to call IPOpt several times for the trial points. The total number of IPOpt iterations is actually really small if you know about interior point algorithms because they're hard to warm start, but only if you make mu small all the time. And here we keep in the mu large and it doesn't change from one to the next. So, okay. And then, okay, so this problem could be solved in what, say 70 seconds. So, yeah, so that is a research project we have been working on.